Welcome to another coding tutorial, and in today's video I'm going to show you how to create the Lorenz attractor. I'm back with another tutorial on chaotic systems, which are systems where slight changes in initial conditions can result in very different motions over time. And I'm inspired to create this tutorial based on a comment left on my previous tutorial on the double pendulum, suggesting that I looked into this thing called strange attractors. And coincidentally, I came across a video by one of my favorite YouTube channels, 3 Blue 1 Brown, where Grant takes us behind the scenes how to use Manim, which is a Python library that he wrote to create beautiful animations for his content. And specifically in this video, he shows us how to use it by visualizing the Lorenz attractor, which is one of the most famous strange attractors. So what are strange attractors? Strange attractors are patterns that emerge by visualizing behaviors of a chaotic system over time, and we can actually do it for the behaviors of a double pendulum by plotting its angles and angular velocity in a phase space over time. But in today's video, I'm actually going to show you how to create a different strange attractor, probably one of the most famous one, if not the most famous one, called the Lorenz attractor, named after Edward Lorenz, a mathematician and a meteorologist who found it back in 1963. The Lorenz attractor is a system of 3 differential equations. And don't be afraid by the term differential equations because we have done it many times before in the past tutorials. So a differential equation is an equation that describes how something changes by linking a quantity like a position or a velocity to its rate of change. So for example, velocity is a rate of change of position and acceleration is a rate of change of velocity. So let's say that when we track the position of a moving ball over time, that position is determined by the changes in velocity, which is also influenced by the changes in acceleration. And here are the 3 differential equations for the Lorenz attractor that describes how 3 variables, x, y, and z, change over time. And sigma, rho, and beta are constants that control the system's behavior, and we can get the iconic butterfly shapes by using these particular or specific values for the 3 constants. Since there are going to be a total of 3 variables, x, y, and z, we're going to be plotting this in a 3D space. So what I'm going to do first is changing from a 2D rendering mode to a 3D rendering mode, and we can do that by providing a third argument into the createCanvas function, WebGL. And then what I'm going to do next is I'm going to declare 6 variables. So x, y, and z. And then how about the 3 constants? Rho, beta, and sigma. Let's start with sigma, rho, and beta. And I'm actually going to give these 3 values the specific values that are going to create the butterfly shape. So 10, 28, and then 8 divided by 3. All right, and then inside draw, we're going to actually write out the 3 differential equations. So dx, let dx to be equals to sigma times y minus x, and then dy equals to x times rho minus z minus y, and then dz is going to be equals to x times y minus beta times z. And then what we need to do now is that we're going to update x, y, and z values based on this change in x, y, and z. So what we can do is we just do x plus equals to dx, y plus equals to dy, and z plus equals to dz. And this is the same exact way that we do to update position based on velocity, right? But actually, before I move forward, what I want to do is also multiplying all of these equations by dt, which is the change of time. Because if you notice here, x, y, and z have a unit of distance, right? But actually, dx here actually have a unit of distance over time. But the reason that we usually don't have to multiply it by dt because usually the change in time is assumed to be 1, but I want it to be smaller. So I'm actually going to multiply all of this by dt. And then now we can actually set dt to be a smaller increment. All right, and let's set dt to be equals to, why don't we do 1, and then I can show you once we change it, what would that changes make to the result. All right, and how about we just plot out all the points, right? So first, how about we create a variable called p, and p is going to be a vector, and a vector is an object that can hold 2 to 3 values, and we're going to use it to hold 3 values, x, y, and z coordinate. So let's do create vector, and we can create a vector using a method called create vector, and then provide the values x, y, and z. And then after that, I'm going to actually create an array called points, and I want to add all of these new points, p, into the array points, and we can do that using a function called push, and push basically just pushing in a new value inside an array. So we're pushing p inside there, and then after that we're going to use a for loop to go through all of the points in the points array. So points dot length I plus plus, and then how about we draw out each of these points. So let's do point, and then we're going to provide points of I dot x, points of I dot y, and then points of I dot z. Let's click run. All right, so 2 things that we actually need to change. The first one is we have not actually given the initial condition for x, y, and z. So how about we set x to be equals to, if we do x equals to 0, y equals to 0, and z equals to 0, what happens is that nothing happens, because everything, the dz, dy, and dz, the x, dy, and dz becomes 0. But let's give it a small value. How about 1? And you can see there are 2 dots here, right? But how about the other dots? So how about we change the value of dt to be smaller? Maybe the increment is too big. How about we do 0.01? And there you go. You can see a bit of a butterfly shape. So what I'm going to do is that I'm going to use a transformation function called scale to actually make it, or zoom in, so make it a bit bigger. All right. And within the WebGL mode, we can actually use a function called orbit control to actually move around the angle, the camera, to actually see the different sides of this pattern. And before we move forward, let's make the screen a little bit wider. All right. Looks pretty neat. So I actually want to change how it looks a little bit before we put all of this inside a class. So first, what I want to do is that instead of plotting all of these points, what I want to do is I actually want to create a line. I'm going to create 2 variables. The first one is called previous, and how about we start I to be equals to 1, so that the previous one would be points of I minus 1. And then we do cur for current one, that would be points of I, and then instead of doing point here, I'm going to delete this. Let's use a line function and provide 6 arguments for the coordinate of the first point and the coordinate of the second point. So it's going to be previous.x, prev.y, and then prev.z, and then cur.x, cur.y, and then cur.z. All right, and let's just try that first. Yay! Okay, so now we have aligned. The second thing I want to do is I also want to draw out a point at the very end, or at the very end of the array. So it's going to be the point where it draws out the shape, basically. So we do in point equals to points of points dot length minus 1. And then we're gonna draw out the point. So endpoint of x, endpoint of y, and endpoint of z. And we probably want it to be bigger, so let's give it a stroke size of 6. And then we want the stroke size for the line to be, no, stroke weight, right? Stroke weight. And we want the line to be the default stroke weight of 1. Okay. All right, so now you can see this endpoint where it draws out the path. Another thing I want to do is I want to cap the number of points that is inside this array. So let's create the cap value for 100. And what we can do is that right here, we're basically creating a bunch of points, right? And we push those points into the points array. But then I'm going to write a conditional statement that says if points.length is greater than max points, then I want to remove a point from the array. And we can use a function called shift. So basically, points.push pushes a point at the end of the array, but then points.shift actually remove a point at the beginning of the array. And then if we do this, oops, what is it? Max points is not defined. Max points. Okay, you can see. Yeah, okay, before we put this inside a class, let's do a few more things. I want the transparency of the end here to be lower. So let me show you what I mean. So I want to change the stroke color based on the stroke transparency based on where it is inside the points array. So we're gonna, let's do alpha. Let's spell it like this because I don't know why it gives me like the bolded font just now. So alpha will be equals to map I between 0 and points length. Then I want it to be valued between 0 and 255. And then we just do stroke of the same color, right? Let's do black and then the alpha value. Actually, let's just do A. Would this work? All right, can you see the transparency kind of go away? Neat, huh? All right, so play around with the colors. We'll make it a little bit more colorful after, but here's the gist. So now I'm gonna put all of this inside a class. So let's come to this arrow here, click the plus sign, and then click create file. How about we call it attractor.js? And then let's reference this file by going to index.html, copy this line of code, change it to attractor.js. All right, so now the new file, the new JavaScript file is referenced. So let's go to attractor.js. We're gonna write a class called Attractor, and inside the constructor function, we're going to I want to put X, Y, and Z, and then I want to put points. All right, I actually want to keep the rest here as global variables. So let's start with that. This.y, this.z. This one is this.x, and I actually want to set x, y, and z as the parameters here. So x, y, and z. And then this has to be this.points. All right, and then we're gonna write two methods, update and display. Okay, so for update, it's basically all of these, right? And also actually this as well. No, down to here. All right, so we're gonna put inside update, and then let's go back here and then just copy and paste the display stuff as well. Okay, and then now what we need to do is we need to make sure that we put in all the this dot, right? So this dot here, this dot, this dot, this dot, this dot, this dot. The ones that I don't put the this dot is because they are global variables, right? So beta z dt, this will be this dot, this dot, this dot, this dot, same here, here and here. All right, and then inside display here, just the points. These are all local variables. Points. All right, I think that's it. Let's go back to Sketch, and how about let me actually put all of this on one line. All right, let's create one attractor. And an attractor is going to be a new attractor object, and we need to give it an initial condition. So let's start with just 1 by 1 by 1. And then here we're going to call the update function and the display function, right? Okay, let's see. Something is not right. What is it? Okay, let's go back. Not this dot sigma. All right. Perfect. Now it's time to create a bunch of them. So we're going to start by changing this into an array. How about we create a variable called num? Let's set it to 20. And then let's write the for loop that goes through I equals to 0, I less than num, I plus plus. We're going to create a bunch of attractors. Attractor of I is going to be a new attractor. Instead of giving one here, I want to give different initial conditions, right? So you can see that it started out close to each other, and then it's going to be very unpredictable. So how about we create a variable called initCont, and how about we set it based on the value of I, but make it even smaller. So I'm actually going to multiply it by 0.05. So I'm going to put in initCont here for the value of x, y, and z. And you can play around with the initial conditions just to see how the shapes evolve. And then here we just need to do the same thing, right? Write the for loop, and then we're going to update and display each of the attractors. Run. Look at that. Starts out the same, and then over time, wow. You can see there's this dot here that just stays here, and that is because this is the dot where the initial condition is equal to 0. So if we don't want this dot, maybe we can do I plus 1. All right. Neat. Okay, now comes the final touches. Let's play around with the color a little bit. So first I want this to be a dark background because I want it to be colorful. So what I'm gonna do is actually going back to the class here, gonna provide the fourth parameter called C for color. And then inside here, instead of 0, we're gonna put in, we can't just put in this.c. So usually we can put in just this.c, but actually that's gonna impact the alpha value here. So what we need to do is that we're gonna put everything inside the function called color. And then I'm going to provide 3 arguments for red, green, and blue. And what we can do is we do red of this.c, green of this.c, and RGB and blue of this.c. And yeah, so now we have that. And if we go back here, what I'm going to do is that I'm going to create this shade of purple to pink. So let's create a variable called C, and C is going to be between, so I want to actually change the values of the red hue, red color. So we're gonna do I plus 1 divided by num. So this is going to range between 1/10 to 1, right? And then multiply it by 255. And then for the green and blue colors, I'm going to put 100 and 255. And then we just need to provide this variable C inside here. And run. Ta-da! Oh, that looks nice. It's also kind of cool because with this specific values for the constant, right, even though it is chaotic, but it remains in this butterfly shape that is really nice. The last thing I want to do with the final color touches is actually, I want the color of the points, the endpoints here, to be white. And that's it. So I hope that you like this tutorial. It is very simple, very start out chaotic, but end up with this very beautiful shape. So I hope that you like this video and also my series on chaotic systems, and give this one a try.